We're finding steady state errors. We went through the general method for that in the previous video. There's a special case where there's an easier way to do it because the general case required sort of multiple steps. We can start to save some of those steps in this particular case. And that particular case is unity feedback. First, I'll define what that means. And secondly, the error will be with respect to R, meaning the tracking error. We're really doing the steady state tracking error. And all unity feedback means is the gain in this feedback path, H, is just 1. And it's just plain old line back here. You could get rid of this box. That's unity feedback. And we already said the error was this, where this big T was the overall transfer function from R to Y. Did a little bit of that algebra. It's this, but if H equals 1, you get rid of this whole term. And the error in the Laplace domain is just this thing. So let's keep doing some things. Let's first find this G sub 0 as the forward path gain with the poles at the origin removed. Well, the big deal is here, we don't have to calculate the whole transfer function anymore. We can just look at the forward path gain, which in that picture will be G sub C times G. That's the forward path gain. And that's all we need. Don't need to calculate the closed loop transfer function anymore. It's going to be done ahead of time. Then the steady state error in the time domain is this limit in the Laplace domain. And what is it? Well, this error is this. Right? It's transfer function times whatever the input R is. Here's the transfer function, and we limit ourselves to one of three kinds of input, or three different kinds of inputs. We can always 1 over S to some power, where the power will be 1, 2, or 3. The final value theorem says multiply by this other S, but we can replace this G sub C G with G sub 0 divided by S to the n. A little bit more algebra. Here's what we have, which ends up one of these 4 possibilities. It's really kind of 3 different possibilities. It's either 0, a non-zero constant, or it's infinite. And these 2 middle ones tell you how to compute a non-zero constant. Put all this in a table in a second. So n is the number of poles at the origin, forward path gain, not the whole closed loop system. And k is the order of the input in the time domain. So it's 0 for a step, power of t, 1 for ramp, 2 for parabola. Now this is kind of a big deal, system type, especially when we're talking about steady state errors. This definition applies whether we're talking about unity feedback or not. System type is the degree of that input polynomial, t, for which the steady state error is a non-zero constant. Case, one of these 2 cases in the middle. And in the case of forward path, in the case of unity feedback. But this definition applies whether it's unity feedback or not. It's the degree of the polynomial in the time domain. Like the parabola is 1/2 t squared. So that degree would be 2. For the unity feedback system, system type is simply n, the number of poles in the forward path gain. number of poles at the origin in the forward path gain. And by the way, all this applies, steady state error, every performance measure we've been talking about only applies to stable systems. We'll talk about stability in the future. For now, we'll assume we're talking about stable systems. So here's that stuff summarized in a table. It's a little bit complicated. You have three types that we consider, 0, 1, or 2, corresponding to a unit step, unit ramp. Well, not necessarily unit. Step, a ramp, and a parabola. They're going to be scaled by the constant A. Here's what they are: step, ramp, and parabola. Here's what the inputs are. Here's the types. These weren't really the inputs. These are the inputs. These are the type of the system. To calculate the errors based on what the error constants are. And we're just now defining them. This is the chart that defines error constants. And the errors themselves are functions of those constants. Case of P for position error, case of B for velocity error, case of A for acceleration. They all are. Type 0 system will have a non-zero constant error even for a step. Infinite errors for ramps and parabolas. Type 1 system has a 0 steady state error for step input, infinite error for a parabola, non-zero constant for a ramp. Type 2, 0 steady state errors for steps and ramps, non-zero constant for a parabola. Here's pictures of what those errors mean. Step input, ramp, parabola, and the error is the difference between the input and the output. Example, let's see. Now we only need the forward path gain. Here it is for this example. The feedback path gain is 1. Otherwise, we couldn't do this. Find the error constants and the steady state errors to a unit, step, ramp, and parabola. Well, P has 1 pole at the origin, so it's type 1. Then we just go back to this chart here, this table here. We're in this row. So we get the K's right here. So for our step, ramp, and parabola, it's infinity, P sub 0 evaluated at 0, and 0. Errors are 0, this non-constant, non-zero constant, and infinity. We got these just from that table on the previous chart. Do this, and then we'll do another video after this. Okay, let's see. Here's the block diagram. It is unity feedback configuration. So all we care about, or all we need, I should say, is this forward path gain, which is the product of both these boxes. Find the error constants and all the same stuff. Unit, step, ramp, and parabola. So the forward path gain is that product. Here's the product. Again, it has a single pole, 1 pole at the origin, forward path gain. Go back to that table, do the calculations. G sub naught is this guy with that S removed and the other S's set to 0. So 5/6, right? And you just use the table. I'll talk about this in another video.